Continuing on with our discussion of mechanical energy, we're going to move past kinetic energy or motion energy and now focus on the second main category, potential energy, and specifically gravitational potential energy. Now, once again, let's have a brief reminder that work, which is a change in energy, can come in three different forms in this class, where we're specifically talking about changes in mechanical energy. We can have a change in kinetic energy where the object speeds up or slows down. We talked about that in the last video. We can also have a change of energy where the energy is stored as potential energy. Or, and we're going to see this a bit more today, we can have energy lost as thermal energy. So before focusing specifically on gravitational potential energy, let's look at potential energy as a whole, which we're always going to be abbreviating with a capital U. Now, that potential really stands for potential for motion energy. That potential energy is stored and can later provide an object with kinetic energy. That potential energy can become kinetic energy. Well, how exactly is it stored? Well, it is stored due to the arrangement of objects with relation to another within a system. So their position, and this is why we could call it, for instance, position energy, their positions relative to each other will affect how much potential energy is stored in that system. But notice we're using the word system here a lot, and that's because for potential energy, we actually require multiple objects. You need at least two objects in your system in order to have potential energy. And so that tells us that if we have only an object by itself, or a system consisting of only a single object, it cannot possess potential energy. It can only possess kinetic energy. And that's something important that we want to remember. Okay, so how exactly do we go about calculating potential energy, though? Well, and there's another way we can define it that's very useful for this sort of idea, which is potential energy is equal to these two different definitions. One, it will be equal to the work done against a conservative force. Or two, it is opposite the work done by a conservative force. But what exactly is a conservative force, and how exactly does this affect things? We've not broken down forces into this distinction before: conservative forces and what we call non-conservative forces. So let's start with conservative forces. A conservative force is a force that if we do work against it, it can be stored as potential energy. But why is it conservative? Why do we use that word? And it's because this potential energy can later be turned into kinetic energy, and so the mechanical energy of the system will be conserved through that process. We are storing as potential energy, it can later become kinetic, but the total amount of mechanical energy does not change. And the examples of conservative forces we're going to deal with in this class are: one, field forces. So that would be the gravitational force, and like the electric force, for instance, the magnetic force would be another example. And two, the spring force, or Fs. Now, what about non-conservative forces? Well, non-conservative forces are, if you do work against them, the energy cannot be stored. And so, typically, what happens to that energy is, rather than us storing it, it is lost, usually as thermal energy. So the mechanical energy of the system is not conserved, because if we lose it as thermal energy, we can't harness it again to get kinetic energy out of it. Thermal energy is not stored, it is quote-unquote lost. And the perfect example of a non-conservative force is friction. So I've been throwing out a lot of terminology now: potential energy, conservative forces, non-conservative forces, doing work against something, by something, etc. It can get a little bit confusing. So let's go through an example and start to see how exactly it breaks down, and it should make things a lot simpler. Let's say we have a 5-kilogram box that's being lifted upward at a constant velocity, and it travels through a distance of 3 meters upward. And we want to determine the work by each force acting on the box, as well as the net work on the box. So let's first by determining the work by each force. Let's draw an FBD for the box. Well, it's going at constant velocity, so the only forces on as it's being lifted will be a force of, we'll say, lift. That could be you could be pushing it upward, or it could be pulled upward. Doesn't matter, but it's a lift force of 50 newtons. And the gravitational force is also 50 newtons. We know that just because it's 5 kilograms times 10 meters per second squared. These have to be equal because it's moving at constant velocity. So if I want the work done by each of these, well, it's moving upward 3 meters, so The force of lift will be in the same direction as the direction of motion, so we'll get 50 newtons times 3 meters. So the work from the lift is 150 joules. Simultaneously, though, if we wanted to know, okay, what is the work from the force of gravity? Well, that would be 50 newtons in the opposite direction of motion. So gravity is going down, the box is going up. So that would be negative 150 joules. And the net work on the box would therefore be, well, 150 joules plus negative 150 joules gives me a net work of 0. And let's pause there for just a second, because remember, we learned last video from the work energy principle that the net work is equal to the change specifically in kinetic energy. So we see that if the net work is 0, the change in kinetic energy should be 0, but that makes sense because this is going at a constant velocity. So the box is not speeding up or slowing down, it's going at the same rate. So its kinetic energy isn't changing. Well, is there a different type of energy that is changing? Okay, well, let's remember, we just talked about two different definitions of how we can figure out how much potential energy there is in some system. And that was specifically definition 1, that delta U is the work done against a conservative force, and definition 2, delta U is opposite to the work done by a conservative force. So let's look at that first definition. Well, based on what we just said a minute ago, the conservative force would in fact be the force of gravity. So what is the work done against that force? Well, that would be the work done by the force of the lift. And so that would be the work of the lift, or we would say, okay, so we've gained 150 joules of potential energy because that was the work done against this conservative force, done against gravity. Otherwise, we could use the second definition. The second definition says it's opposite the work done by a conservative force. Well, what is the work done by a conservative force? That would be the work due to gravity, which is negative 150 joules. But we want the opposite of that. So we're going to multiply that by -1. And once again, we get 150 joules. And we see for both of these situations that the number is the same. So the system has gained 150 joules of potential energy as it is lifted these 3 meters. Well, what type of potential energy is that? Well, because we're doing work against gravity, against the gravitational force, this is actually going to be the change in gravitational potential energy. So the change in gravitational potential energy was a result of doing work against gravity, or in other words, opposite the work done by gravity. Now, right here, although this says WG, keep in mind that really the work done against gravity was that work of lift. And if we were doing that at a constant velocity, that would be, what is the force we're overcoming? It's the gravitational force. So we're doing work against the gravitational force. So that work is going to be equal to the gravitational force times the distance, if that's the only thing we're thinking about here. Well, how would we calculate gravitational force? We just do mg, the mass times g. And specifically, if we are doing work against gravity in either direction, it's going to be a change in vertical position. The distance horizontally is not going to matter. We're only going to change if the object is moving up or down. And in fact, this is the equation for a change in gravitational potential energy. So the gravitational potential energy, or UG, is the stored energy that results from the position of an object in a gravitational field. So in other words, if I have an object in a gravitational field of another object, it will have, the system will have gravitational potential energy. If I change its position in that gravitational field, specifically, if I change the distance between it and the object generating the field, well, then we are going to be storing gravitational potential energy. And so that equation was delta UG equals mg delta y, where delta UG is the change in gravitational potential energy in joules, m is the mass in kilograms, the mass of the object in the field, g is the acceleration due to gravity, which we can approximate as 10 meters per second squared, and delta y is specifically the change in vertical position, in this case above the earth, or in other words, the change in height in meters. So what this tells us, because typically the masses of our object aren't going to change. If you want to change the gravitational potential energy of an object, you just need to move it up or down. If I move an object upward, it gains gravitational potential energy. If I move it downward, the system loses gravitational potential energy. So let's look at an example. Let's say we have a 60 kilogram student riding an elevator from the first to the third story of a building, and in that process, they rise 35 meters. And so we've got three different questions here. How much gravitational potential energy does the student gain in this process? How much gravitational potential energy does the student Earth system gain in this process? And what is the gravitational potential energy of the system at the beginning? So when the student's on the first floor, and at the end when the student's at the third floor of this elevator ride. Alright, so let's go through these one at a time. Let's start off with number one. How much gravitational potential energy does the student gain? And you'd probably think, okay, well, I'm going to use delta UG equals mg delta y. And I've got the mass of the student times 10 times the change in vertical position, or 35 meters. You multiply those together in your calculator, and we get delta UG is 21,000 joules. A big number, but remember, a joule's not really that much energy. Unfortunately, this is actually incorrect. And why is this incorrect? Well, if I have an object, how can it gain or lose gravitational potential energy? It must be moving around in a gravitational field. So, we need something else generating that field to be there, or else we can't have any gain or loss in gravitational potential energy. So right now we're focusing on a system that is only the student. If we're only looking at the student, well, there's nothing generating a gravitational field for the student to be in, so the system of only the student can't have gravitational potential energy. Remember, we said potential energy requires multiple objects in their position in relation to each other. So actually, the answer for question one would simply be 0. That the change gravitational potential energy of the student alone is 0 because Earth is not part of the system. We have to include the Earth because the Earth is generating the field that the student is moving around in. It's their interaction that generates this energy. So then how much gravitational potential energy does the student Earth system gain? Okay, now we have both parts of the system that we need, so this whole calculation we did right here, that actually is the right answer for number 2. The right answer would be 21,000 joules. So student alone gains nothing. The system of the student and the Earth gains 21,000 joules. Lastly, what is the gravitational potential energy of the system at the beginning and end of this elevator ride? Because we saw that the change is 21,000 joules, so what would be the gravitational potential energy at these 2 points, which we would say is mg y naught and mg y, the initial height and the final height? Well, the thing is, though, is what do we define as y naught? Because, we could say that that initial height is 0. But, they're actually probably not exactly at ground level. Maybe there's at least a few inches between them and the ground of, pavement and floor and everything else. And what if this building was like on a mountain? And if it was on a mountain, well then even though they're on the first floor, they're way above what we would consider to be the standard surface of the Earth. So this can be really, really up for interpretation. So, how do we handle this? Well, first off, what really matters is the change. The change in gravitational potential energy is more important than the value at the beginning and the end. But if we're going to go ahead and set values for the beginning and the end, I will go ahead and tell you, to make our life easier, it is best if we go ahead and just set, okay, whatever my lowest height was, I'm going to say was y equals 0. I'm just going to establish that. I set y equals 0 at the baseline where I started. And that way, you can just say, oh, okay, we've gained 21,000 joules. Boom, I'm done. So what are our takeaways for gravitational potential energy? Well, one, I conceptually define what potential energy is. That it's this position energy between objects in the system, that it's stored energy due to that arrangement, and additionally, making sure we remember that it's either the work done against a conservative force or the work done by a conservative force. Can we distinguish between conservative and non-conservative forces? Can we identify when gravitational potential energy is present in a system? And additionally, can we calculate changes in gravitational potential energy using the equation delta UG equals mg delta y?